Okay, last night you were asked to read and define precision and accuracy in your notebook. So those definitions should be somewhere in your notes already. Before we get to those definitions, I want to discuss a measurement. So let's first start by giving me an example of a measurement. So just shout one out. Good. I heard 9.7 seconds, I heard. I got good hearing. I could hear somebody say that in the back. All right, give me another example of a measurement. Okay, that works. 77 degrees Fahrenheit. And I think I heard somebody say something like close to like 28 centimeters or inches. Something similar to that. So those are examples of measurements. So in each example that you've given, 9.7 seconds, 77 degrees Fahrenheit, 28 centimeters, there are parts that every single measurement should have. So what do they have in common? What's one thing that all measurements have in common? Excellent, a number, a value. So every single measurement must have some numerical value, a number. That's not it. What's the second thing that you see up here in the examples? Excellent. They have a label, or sometimes you call it a unit. What's the third thing that all measurements have? This one's going to be harder. I'll have to ask the sub to write in the notes if anybody came up with this one, because this is more challenging. All measurements have a statement of precision. They're telling you something about the instrument that recorded that measurement. So for an example, I'll take the first one, 9.7 seconds. That could be, how long somebody ran a race, a swimmer. If they have a stopwatch that can tell them 9.7 seconds, but I've seen stopwatches that tell you 9.77 seconds. Right? Or I've watched the Olympics where they have one that is 9.7741 seconds. Those numbers right there are showing you different measurements have different statements of precision. And it's all based upon what kind of stopwatch were you using. Were you swimming and I was going, okay, ready? I'm going to time you. 1 Mississippi, 2 Mississippi, 3 Mississippi. Oh, good. You got about 10 seconds. I'm going to round that off. 10 Mississippis. That's not very precise. That's not a really good way to measure somebody swimming. Or do you have an Olympic timer that is telling out to that many places? Statement of precision. Now, what that's doing is it's leading back to your reading last night, the definition of precision versus accuracy. Precision has to do with the instrument, how reliable something is, how reproducible something is. So for example, if you use a triple beam balance to find the mass of something, and you take an object, a rock, you put a book on there, and you find the mass of it and you record it, whatever the value is. And then you take it off, you try it again, right? And you get the same exact answer. You do it 5 times, you get the same exact answer. Does that mean that you are accurate? Not necessarily. Accuracy is something different. Accuracy is the actual value. So like if this was the rock and you found its mass 5 times and you were really close every single time, like let's just take 94.3 grams, 94.5 grams, 94.7 grams. You're pretty precise. You're getting close to the same value. Here's the problem. That rock does not have a mass of 94 grams. It actually has a mass of 87.2 grams. Well, can you think of a reason why you were not accurate? Remember anything about triple beam balances, you're supposed to make sure that the thing is set to 0 first. If you forgot to do that, you would not be accurate, but yet, boy, you're good on a tri-beam, you're pretty precise. Precision versus accuracy. When we discuss accuracy, we want to compare our value, maybe you average them, and you want to compare it to what is known as the accepted or the actual value. Everyone in here should remember from Earth Science class how to compare a measurement to an accepted or an actual value. It is called percent error or percent deviation. The formula is on the last page of your reference tables. If you want to pause for a moment and you want to write that into your notes, you can. You will, in lab class, have to use the percent error formula to see how, in lab, your values compare to the accepted one. How accurate are you? So what I'm going to ask the sub to do right now is, yes, you can go ahead and add that formula in if you need to, but I'm going to ask the sub to hand out this paper right here, and for a few minutes I want you to use the terms accuracy and precision to describe these 4 dartboards. Look at the examples. Does it show high accuracy or low accuracy? High precision, low precision. Try using words to describe those 4, and then we'll come back in a minute. Okay, so just a quick check and see how'd you do on the targets, right? With the idea that the bullseye is where you want to be, right? Take a look at number 1. They're not anywhere near the bullseye, right? They have poor accuracy or low accuracy. They're way over in left field, right? And they're not very precise because their darts are scattered all over the place. So I'd say low accuracy, low precision, or poor for each one. Look at number 2. They're around the bullseye, so they're somewhat accurate. I mean, their accuracy is pretty good or okay. However, they don't keep hitting the same spot. They don't keep reproducing the same value, so they have poor precision. So number 2, poor precision, but okay or pretty good accuracy. Look at number 3. Wow, are they precise. They clump all their darts in the same spot. They keep getting the same reproducible value. It's kind of like that triple beam balance that wasn't 0. So good precision, but they're not near the bullseye. So number 3 is poor accuracy, good precision. And number 4, finally, we have good or excellent for both. They are accurate because they're all near the center, the bullseye, and they're really precise. They keep getting the same value again and again. All right, next thing I want to do is I want to use my smartboard, but remember I can't use it. I'm only using it as a projector. But I want to introduce the concept of significant figures. Significant figures is a way of showing a statement of precision based on an instrument. So if I use my meter stick to measure the length of something, or, as a great example, let me show you with this meter stick. And instead of holding up like a yellow piece of paper to see like the length of it, what I'm going to do is there's an arrow on there to say, okay, from 0 out to that arrow, what is the length? So that is the point I'm looking at. Well, if you look at this meter stick, you can see it only counts by tens. 10, 20, 30, 40, 50. So if you read that value, you know what it's 20. It's not quite 30, it's 20 something. So if you want to take a measurement, what you have to do is you have to say 20 and then estimate one more place. You have to say that the length of that is 23, whatever the label is, 23 centimeters. Let's say this is a centimeter ruler. That tells you that there's only 2 significant digits there, the 20 and the 3, and that's it, 23. How about this ruler? This ruler, again, is counting by tens, but it also has the mark in between, counting by fives now. So you can see 0, 5, 10, 15, 20, 25, 30, and you look at the arrow to show you the length. You go look at it, you know it is greater than 20. It's not quite 25. So again, the only thing you can say about this ruler is that the length of that arrow is 23 centimeters. So again, it has only 2 significant digits. This ruler is not going to help you much more than the top ruler. Either one is giving you 2 significant digits. That's like me timing you run a race going 1 Mississippi, 2 Mississippi. Not a very precise instrument, or excuse me, an instrument that's going to give you very precise data. Let's take a look at this ruler. Now what I see is it's got 10, 20, and 30 again marked off, but now it's counting by ones. So you can go 10, 11, 12, 13, 14, all the way up to 20, 21, 22, 23. So now when you look at it, you can say, oh, I definitely know it's 20. It's past the 20. But now you can see that it is near the 3rd mark. So you can say that, yes, I'm certain, all right, that there is a 3 there. It's 23. But with significant figures, we always have to estimate one more place, just like we did up here. We knew it was more than 20. We weren't sure, so we guessed 23. So here you need to do the same thing to show that there's one more statement there, one more value that you're uncertain of. It's 23, and now it's just a guessing game. Do you think it's exactly on the 3? Is it a little bit above, a little bit below? I think it's exactly on the 23. So in terms of significant figures, I would write 23.0 centimeters. That has 3 significant digits. 20, yeah, I'm certain of it. 3, I'm certain of it. 0.0, I don't know, I think it's about lined up. Now somebody on one side of the room, just from their vision, could say, I think it's a little bit past, and they could have said 23.2. That would have been a valid measurement. Again, it would have 3 significant figures. Somebody on this side of the room, looking at it, might think it looks like it's a little bit less, 22.9. That's still okay. 2 people using the same instrument can come up with 2 slightly different measurements. That's where your human interpretation comes into play. 3 significant figures. Let me show you one more. This ruler is going to have a lot more to it. Let's make sure that you guys can see all of that. Okay? With the camera. What this is trying to show you is that, again, you're counting by tens, 20, 30, 40, but you also have the ones, 21, 22, 23, but then between 23 and 24, there are 9 little marks to show you the tenths place. So again, if you're going to use this ruler that's got a lot more markings, you know, and we have some instruments that do that, you're going to have a lot more values in your measurement. So on this one, you know it's 20, you know it's at least 23 because it's past the 3. Right? Now you know that it's at the second mark past the 23, so now you know it's 23.2, but with sig figs, you must always estimate one more place. You want one place of uncertainty. So you would say it's 23.2, and then it's up to your guess. Do you think it's exactly on the mark? 23.20? If you say that, then you would now have 4 significant digits in your measurement, 23.20. Maybe you thought it was a little bit past, 23.21. Doesn't matter. It's still going to have 4 significant digits. It's still a valid measurement using that instrument tool. Notice, a lot more lines, you're going to have a lot more data, a lot more places. Hardly any lines, you're not going to have a lot of data. So when we use a ruler, meter stick, triple beam balance in the lab, I'm going to want you to remember this, that you always read what is given and then you estimate one more place. That's a skill that we're going to practice in lab quite a bit. Now to finish up, that's going to lead into our rules for significant figures for today. So the next thing I want to discuss is the rules for significant figures. So if you are given a measurement that's already been taken, somebody had a ruler, triple beam balance, they write down a measurement for you, you look at it, you should be able to pick out how many of those values are significant versus just maybe a placeholder. There's going to be 4 rules, and I'm going to discuss examples for each rule. Make sure you copy it on the examples. Rule number 1, non-zero digits are significant. So for an example, 743.2 centimeters. There's no zeros there. So every single number counts. The 7, the 4, the 3, and the 0.2. So there are 4 significant values in 743.2 centimeters. So basically what rule number 1 is telling you about is you only stress over the zeros. It's the zeros that make your life complicated. Let's go to step number 2. Zeros that are between 2 other sig figs are always going to be significant. I call it the sandwich rule. Let's look at this example right here, 403.1 grams. That 0 is sandwiched between a 4 and a 3, so it counts. It's significant. So in this value, you got 1, 2, 3, 4 sig figs. This one right here, these zeros are not sandwiched, but this 0 is between a 7 and a 2. That 0 is significant because of rule number 2. So I've got 1, 2, 3, 4 significant figures in 0.07022 kilometers. 4 sig figs in either one. That is rule number 2. Rule number 3. This is for zeros that appear at the end of a number. They're kind of trailing. They are going to be significant under 2 conditions. Condition number 1, the zeros at the end are significant if they're followed by a decimal point and they're following a significant digit. So for example, this 0 right here will be significant because it's following the numbers. It's at the end. It's followed by a decimal point. Believe it or not, when you measure precisely, there is a difference between 790 centimeters and 790 decimal point centimeters. Up until this point in your life, you probably thought the two were the same thing. But in terms of measuring, there is a different level of precision there. This value has 3 sig figs. The second case when a 0 will be significant at the end is if it is to the right of the decimal point as a final digit. So why would you bother putting it at the end to the right of a decimal point unless it was significant? So the example to show here is like what we were just doing with the ruler with hardly any lines. 28.0 centimeters. That 0 is significant. You were estimating. That was the place of uncertainty. So there's a difference between 28 centimeters and 28.0 centimeters. Again, up until higher level math and science, they probably don't even care. You don't even think anything of them. Sig figs, significant figures, that is different. And then the last rule, number 4, zeros that are used solely for spacing the decimal point, so all you're doing is to space something, placeholder, are never significant. So if you look at the 2 examples on the bottom, 0.0078 milliliters. That's a very small amount of fluid. If you're going to tell somebody that, you have to put those zeros in there to kick the 7 and the 8 way over. So they are not significant, they are just placeholders. This value has just 2 sig figs, the 7 and the 8. If you don't put those zeros in there, you have 78 milliliters, and 78 milliliters is a lot more than that value. So you're forced to put them in. Look at this example, 3,400 kilograms. You have a large mass. You need to tell somebody 3,400 kilograms. If you don't put the zeros in, you got 34 kilograms. That's not quite the picture of what you wanted to describe. So you're forced to put those zeros in as placeholders. They are not significant. This value has only 2 significant figures. Now, thinking about another rule that we said, what happens if I put a decimal point there? If I add a decimal point, I am now up to rule 3-1. And now, since it's followed by a decimal point, those zeros would be significant, and now I would have 4 sig figs, because they'd be similar to this one. So just putting a decimal in can change your measurement. All right, I believe that's the rules for sig figs. Tonight you're going to practice that with the significant figures homework sheet, section number 1 through 20. Oh, and when you get to it, if there is a number that is in scientific notation, ignore the last part of the scientific notation and just look at the very first part. So if it says 2.10 times 10 to the third, ignore the times 10 to the third and just look at 2.10 and figure out how many sig figs in 2.10. That will help you with your homework. So you're going to do 20 on that sheet and then 3 on the precision and accuracy sheet from last night, and check the board. It's written